So, welcome to the lesson on subscript notation. So, the objective of this lesson is to be familiar with different forms of notations, and subscript notation provides us with a very succinct and brief way of writing expressions. During the course of this NPTEL MOOC on transport phenomena and materials, we will be doing quite a bit of algebra, and the number of expressions we use can be reduced if we use subscript notation. So, here are the simple rules about the subscript notation. It is also referred to as the Cartesian summation convention, and this has been proposed by Ricci long back as a mathematician, and as it has been popularized by Einstein because he used it in many of his papers later on, and the number of rules are quite few. So, you should be able to commit them to your memory and then use them as we do the derivations later on. So, the rules are as follows. Subscripts which come below the term that we are using are called dummy subscripts if they are repeated. For example, you write an expression, and if we happen to write two subscripts that are same, then here I is a dummy subscript. And in case I have subscripts that are not repeated, let us say A, and then I write two subscripts I and J, then both I and J are free subscripts. So, here in this example, for example, I and J are both free subscripts, and in the first example we had I as the dummy subscript, and these can come anywhere in the expression. What we mean by that is they could come in the numerator or denominator, and the terms can be written as follows. For example, you could write an expression like this. So, this is an expression which is valid because it does have the subscripts that are different, and numerator or denominator does not matter, and we can see that there are two free subscripts in this notation. We have I and J as free subscripts, and what we mean by the summation, here we mentioned summed. What we mean by that is, whenever you see an expression of this type, what we meant was that the I has to be summed, and usually it is summed over 1 to 3. The reason is we live in a 3-dimensional world, most of us in engineering, and therefore we use the summation over the 3-dimensional space. So, this expression what we wrote just now is nothing but summation as follows. So, it would be A11 plus A22 plus A33. So, as you can see immediately that when we expand, we have several terms, but then when we write it using the summation convention, the expression is quite small. So, this much will suffice to write what we otherwise write in this manner. So, this is where the savings comes as making the expressions brief. And the fourth rule is about the comma. So, what we mean by that is, whenever there is a comma, the differentiation is implied, and it is also implied that the differentiation with respect to the location. So, for example, when you write A comma I, what we mean by that is dou A by dou xi. So, it is implied that the differentiation is with respect to x, where x is the distance variable, and I is the subscript here, which is free subscript because there is no repetition there. And whenever we write any expression, we would like to have the subscripts, free subscripts matching for every term, and including for the left hand side and the right hand side. So, that is what is meant by the fifth rule. We say that on both sides, left hand side and the right hand side of the equal to sign, the number of subscripts should be matching. The free subscript should match. It does not matter the dummy subscript which ones we use in different terms. So, technically we could use different dummy subscripts in different terms on the same side of the equal to sign. So, that is allowed. So, let us take some examples. So, here is where we see the savings in the notation. So, what have we written here? We have written a vector. Vector is u, and we normally use this kind of a notation in our engineering classes, a vector u is denoted like that. And if you want to express vector u as its components, u1, u2, u3 along the 3 axes, then you do have some vector u, and the 3 components are written as u1, u2, u3, and so the vector can also be written as a set of 3 numbers u1, u2, u3. And here is where the savings will come in terms of the subscript notation. U subscript I is adequate to indicate the entire expression that we are showing here. So, this is adequate to imply the entire expression that we have shown here. So, you can see that the amount of writing is reduced, and one subscript is there to indicate that it is a vector with 3 terms. Note that the number of free subscripts here is 1, and the number of terms is 3. So, the number of terms is 3 raised to the power of 1, and here this is basically the number of free subscripts, and this 3 is because we are talking about these quantities in 3-dimensional world. Now, there are many quantities in engineering which require more than 3 components. So, vectors require 3 components, but there are many things that require more than 3. Tensors, second order tensors require 9 components, and we do have matrices also requiring 9 components when we look at many of the transformations that we will be doing in the classes further on. And so, if you take a matrix like this A, for example, the matrix A, then the 9 components have to be written tediously in this fashion, and you could see that the entire set of 9 elements is indicated by a very simple expression Aij. You can see that the 2 subscripts are not repeating. So, both I and j are free subscripts. So, there are 2 free subscripts, they are namely I and j, and you can see that the number of elements on the right hand side are 3 raised to the power of 2, that is 9 elements. Okay. So, this is how we could save the writing. 9 elements are written with just one symbol A subscript ij, where I and j are the free subscripts. So, here we just practice what we have seen till now. Let us say we are restricting ourselves to the 3-dimensional space, and I am asking how many components are there for each of these quantities. So, you could see that the first quantity is ui. So, you have basically only one, let us indicate the free indices. We have only one free index I, and because it is only one, so 3 raised to the power of 1, and so therefore, there must be 3 components. Okay. So, u is a vector and there are 3 components. Subscript I indicates immediately that there are 3 components. So, here we have sigma subscript ij, and there are 2 subscripts, and which means that we must have 9 components. And the savings comes even more when we go to higher dimensional quantities. So, here we have got epsilon ijk, and the free subscripts are all the 3 ijk, all are free subscripts. So, we are supposed to have 27 components, and imagine having to write 27 components with epsilon 111, epsilon 112, etc. So, that is going to be very tedious. So, writing it as epsilon ijk would be very simple, and mu ijkl is a quantity which has 4 free indices, and it would mean that there are 81 components. And you could imagine that doing algebra with 81 components would be quite tedious. So, using the subscript notation would be quite useful when we take quantities which have many subscripts like this. So, what do these quantities mean? How are they useful to us? Do we encounter them in our subject, namely transport phenomena? These things will become clear as we go along, but let me preempt myself by indicating that these things are going to come in the following manner. For example, we are going to see u because we are going to look at the fluid flow, and therefore, the fluid flow represented as a velocity will be represented with this quantity, and sigma will be coming in because we are going to look at the stress. Okay. So, shear stress causing the fluid flow will be represented with this quantity, and therefore, we are going to use that at some point. epsilon is going to be used because we want to convert the expressions that will be using the curl operator, and mu is basically going to be for us the viscosity and in the most general form, and it is going to require 81 components, but then later on we will see how we were able to reduce all the 81 to just one component for an isotropic material like liquids. So we now go further to practice further. Now we have not one parameter, but we have two parameters. So look at the first expression and see, analyze what is required. So you got ui and vi. So how many free indices or free subscripts are there? None, because both are repeated. So it implies that 3h to the power of 0, there is only one component here. And what is that component? It is nothing but u1 v1 plus u2 v2 plus u3 v3. And you might already be familiar, this is nothing but the dot product of two vectors u and v, and that is just one number that you get. You can see the savings in terms of the writing. So such a large expression is going to be represented by a very brief expression ui vi. Take a expression like u aij and bij, it is the same thing here also. So number of free indices are none, so which means that there is just one component, and when we try to expand this, then we would see the savings. You can see that there are going to be 9 elements. So you would have a11 b11 plus a12 b12 plus a13 b13 plus so on. So you could see that all the indices are repeated, and you would just get one number when we multiply all these quantities. And here, for example, you can see that the k is repeating and iij are not repeating. So which means that there are two free indices, and this would mean that there will be 9 components. So you could then write, for example, this expression as follows: d I j k e k as some other quantity, maybe c I j, so that the free indices are matching on both sides, and the summation is over the index k, and that you could write it as k is equal to 1 to 3. So this is the expression that we meant by this. So you could see that such an expression is written very simply. So what we have done here is basically two things. K is the dummy index, so we are summing up over that dummy index, and I and j are the free indices. So we are then mapping over to another quantity c, which has the same free indices I and j. So here the last quantity epsilon ijk and sigma ij, you can see that I and j are repeating. So therefore the only index that is free is one free index, which is basically k, and therefore there will be 3 components. So if there is only one free index k, then you could write this expression as follows. You could write it as, for example, you could write it as follows: I j k sigma I j is equal to, for example, p k. So here you can see that I and j are repeated, so they both are dummy indices. K is a free index, and because it is only one index, then it means that it is a vector we are talking about, and the expression really would be like this. Okay. And when we sum it up and express the left hand side, then we would get the elements of p for each value of k that we are going to write. Okay, so such a large expression is then written in a very simple form here, and that exactly is the purpose of subscript notation. So you can see that this is what is mapping up here. Okay. So these are the benefits of subscript notation, and every rule of the subscript notation that we have seen must be kept in mind while manipulating these expressions. So we can go further here and look at what are the free indices and what are the dummy indices. So you can see that k and l are repeated. So I and j are the free indices here, and K and L are the dummy. So, which means that this is a quantity which is like a second order tensor, and it would have 9 components because there are 2 free indices. So, 9 components. So, which means that you could also write this quantity as like this: A, I and J are free indices, I keep them, and S, I, J, K, L, sigma K L. So, this is what you could write, and what we meant by the dummy indices is as follows. What we meant was this: A I J is equal to sigma S I J K L So, this is the expression what we meant by this. Okay. Similarly, here also we could analyze what is happening. The second expression is C I J K L, E I J and E K L. You could see that I J are repeated, K L also are repeated, which means that there are no free indices, which means that this must be just a number. In fact, it is only a scalar, and this incidentally happens to be an expression that will give you the energy, and you could then write it to be some quantity, and you may want to just put something like that. We will not put any subscript there because there are no free subscripts on the right hand side, and therefore, there should be none on the left hand side as well. Similarly, here in the last expression we have on this slide, I J K L are the subscripts for chi, and then there is a vector that is coming 3 times with subscripts j and k and l. I is the free subscript. So, you could write this as, for example, pi, and what we mean by the matching of the indices j, k, l in 2 different terms is that there is a summation that is being done over each of them, j, k and l. This is what we meant by that expression. So, it is a vector, by the way. So, you could see that here is a situation where this expression is actually a vector, this expression is a scalar, and this expression is a tensor of order 2. So, you can generate vectors, scalars and tensors of any order by using subscript notation, which takes into account multiple components, and choosing some as free indices and some as dummy indices, you could generate these expressions. So, here we can see that we are now making use of one more rule of the subscript notation, namely the subscripts can come anywhere. So, in this case we are getting the subscripts in the denominator. So, let us see what we meant by this expression. So, the first expression does not have any free subscript, both the indices are I. So, which means that this must be a scalar, and when we expand this, what we meant by this expression is nothing but this expression, which is nothing but W1 by dou x1 plus W2 by dou x2 plus W3 by dou x3, which is nothing but the divergence of the vector u, which is actually a scalar. So, you could see that this expression is giving you a very brief way of writing the divergence expression that is here. Similarly, here the same thing, but you have got one free index. The j index is dummy, I is a free index. So, this must be a vector, and let us choose this vector to be p, and the free index is I. So, pi, the vector pi is equal to dou sigma I j by dou x j, and because j is the dummy index, this would mean that this is what we meant by this expression, which means that we could then sum up over the j index and get each value of p. So, you could then ask what would be the value of p1. Okay, there are 3 values of p, p1, p2, p3 for each values of I going from 1 to 3. So, what is p1? p1 is nothing but this. This is what is p1, and you could then expand this with the j, and you can get what is that expression. That is nothing but dou sigma 1 1 by dou x1 plus dou sigma 1 2 by dou x2 plus dou sigma 1 3 by dou x3. Similarly, we could write for p2, which will be dou sigma 2 1 by dou x1 plus dou sigma 2 2 by dou x2 plus dou sigma 2 3 by dou x3, and so on for p3. So, you could see that the vector p can be written in a very succinct form in this manner by using the indices both in the numerator and denominator here. What would be this quantity? This quantity, there are 2 subscripts, both I and j are free, and there are no dummy subscripts. So, this must be something of the order 2. So, it has 2 free subscripts. So, it must be a tensor of order 2. So, you could write this guy as aij. So, for each value of I and j, you could write what would be the expression. So, let me write it here. What would be a12 is nothing but dou u1 by dou x2, and so on. So, you have got basically this equation what I wrote just now is nothing but 9 equations, because for each element of the matrix A, we have got an expression on the right hand side. So, there are 9 expressions that are written. So, what we wrote here is actually 9 equations. When we wrote here p, pi is equal to, if write this as equation, then these are basically 3 equations. And when we wrote here, for example, this quantity, this is just 1 equation. So, in subscript notation, when we write an equation, though we may see that there is only one expression, depending upon the number of free subscripts, actually there will be large number of equations that will be coming up. You could see that the same equation very simply written would actually mean either 1 equation or 3 or 9, okay, depending upon the number of free subscripts. Okay. So, what about the last quantity? The last quantity, we have expanded the complexity a little bit by putting 2 quantities side by side. You could see that in the first term you have got n that is matching, which means that is a dummy index. The second also the same thing, n is matching. The free index is m. So, this must be a quantity which is having one free subscript, which is m, and I may want to choose the quantity to be like this. So, this must be the equation we can write, and for each value of m, we can write what would be the expression on the left hand side by summing up over n going from 1 to 3. And how many equations do we have here? We have got 3 equations, okay, which basically are for values of m going from 1 to 3. Okay. And the 2 terms are evaluated and then summed up. So, the plus sign does not have any significance apart from adding 2 terms, just like you add 2 numbers. Okay. So, the comma symbol will then have to be practiced. So, here we see how is it used. The comma is basically an implicit assumption that we are going to use it for differentiation. So, here is where it is indicated. So, the comma is coming here, it means that we are going to differentiate with respect to the space variable. The I index has to match with respect to the distance variable we are using for the differentiation. So, you could see that the 1 comma there is actually substituting for dou by dou x, which is there are 3 symbols that are sitting there, and comma is just 1 symbol. So, you have got a savings in amount of writing you are supposed to do there. So, what we mean by that is you could write expressions like this. So, whatever you have written here, which is nothing but the gradient of phi, is written in this form. Okay. So, you could write what is the gradient? Gradient of phi you would write this way, or you would write it in this way, but you could write it without any other symbol. The nabla symbol that is here is not used. You could actually just put a comma there and then I here, and this is enough to just say that it is a gradient of phi with respect to the distance variable xi. and when you combine all the rules, namely the free subscript rules, the dummy subscript rule, the rule that allows the subscript to come in both numerator and denominator, and the comma indicating the differentiation. When you combine all these things, then fairly complex expression can be written in a very succinct form using the subscript notation. Okay, so we can see how we are using this same subscript notation even for operators. So here, if you see the way it is written somewhat like it is a vector. You could see that I am just writing below a vector ui, and then I am writing it the way we have seen, u1 plus u2 plus u3. So you could see that as if nabla has a component dou by dou x1 along the x1 direction, dou by dou x2 along the x2 direction, and dou by dou x3 along x3 direction. We are writing it with a subscript I, but one difference is that this is for a vector and this is an operator. Okay. So while vector can come anywhere in an expression because it is just a bunch of numbers, and then the way we multiply numbers there is a commutativity, operators have to be moved around a little bit carefully because they are going to operate on what is on the right hand side of their things. So for example, whenever you have an expression like this, okay, when you have something like this and an operator and then something else, this is acting on this. So this, if you have something else, you could switch them off back and forth, but you should not move this. This is wrong because nabla as an operator works on B and it should not be moved on the left hand side. It can be operating only on what is on the right hand side. So there are certain cares that you must take when you are using the subscript notation along with the operators. Though we write as if the operators are like any other quantity, we must take care of that. But keeping that in mind, we can then use this concept to write large expressions even much simpler. You could see what are we writing here. We are writing the gradient phi using the operator, and then we have put the symbol I there, pretending that the operator is also indicated with a subscript and treating it on par with a vector. Okay. And if you then combine these, then we could write expressions that give some more meaning. For example, this quantity is the divergence as we have just mentioned ahead in this class, and the divergence of a vector u is written by this symbol, and in subscript notation it is written in a very succinct form like this. Okay. So this involves only 3 symbols. Here you have got an operator, a vector, and then a dot showing that it is a dot product, etc. All of that is actually implied. So the way it is implied is as follows. When you write something like that, I comma I, the fact that there are repeated indices, okay, so I index being repeated implies that we are talking about a dot product here. Okay, so there is a dot coming in there. That dot is indicated by this because we are going to sum up over the index I, and then this comma implies that we have got a differentiation that we are going to indicate here. So very simply, the repetition of the index and the comma between them indicates the sense that is conveyed by the divergence here. So if this is what we have understood by applying this for a vector u, then what does it mean by an expression like this here below? So let us see what this means. So you see here this expression, the first expression sigma ij is not a vector, it is a tensor of order 2, it is a bunch of 9 numbers, and then we have got 2 subscripts that are repeated, j is repeated, so the free subscript is I. So let us say that is pi. So pi is nothing but this expression we are talking about. And what is this? The comma should indicate that there is a differentiation. So what we mean by is this. Now what subscript should I use for the x? The subscript that is to be used is what is repeated and after the comma. So this is what we meant by this expression. Okay. And how to get the elements, individual elements of P? We can just write element by element, we could write P1 and P2 and P3 as follows. So, you could write it this way. So, dou sigma Pi P dou 1 1 by dou x1 plus dou sigma 1 2 by dou x2 plus dou sigma 3 by dou x3. So, there is a sense of divergence that is coming in, but there is an additional dimension because you have got these as just elements of a vector P. Okay. So, you could think of this as divergence applied to higher order quantities, namely the tensors. So, subscript notation allows you to take the definitions that we know on vectors to tensors without much algebra, and the subscript notation also allows you to then interpret these in terms of the complete forms. The complete forms are quite tedious, whereas the subscript notation is quite succinct. So, let us practice that and write what this means. So, what is this quantity u I comma j? So, we have got here two free indices, both I and j are free. So, this should imply that we have got 9 elements or 9 components of this quantity, and what are those? So, what we mean by that can be written in this fashion. So, the first element 1 1. So, dou u1 by dou x1. Second element is 1 2. So, dou u1 by dou x2. Third one is 1 3, dou u1 by dou x3. Similarly, dou u2 by dou x1, dou u2 by dou x2, dou u3 by So, this is a matrix that we implied. So, let me just correct this. Okay. So, this is what we meant. So, such a large expression with numerators and denominators and dou sitting on both sides, this kind of a large expression is just indicated by a very simple expression here, and this has a meaning also. As we will discover later on in this course, this is nothing but the gradient velocity gradient tensor. Okay. So, the subscript notation allows you to write this expression in such a simple fashion. So, here what are we doing actually? We are just simply seeing that whenever there are free indices, we vary them over 1 2 3 and then list out all the elements, and whenever the free indices are not there, whenever there are dummy indices, we just sum it up. So, we are just following the subscript notation rules diligently, element by element and index by index. Okay. So, here we are going to now see whether we can identify any errors in the subscript notation. Now that these expressions are using all the rules that we have practiced till now, we should be able to identify some errors here. So, let us see if we can identify. The left hand side has the free index I. Here you have got free index is I. The first term, you can see that the dummy index is there I, and then the third term is free index is j. The free index on the left hand is I, the free index on the right hand is j. So, there is a mistake there. So, how do we correct? So, the way to correct is this quantity should then be changed to Aj, then it will be fine. So, Aj is equal to a scalar quantity plus Bj, and that would be valid. Okay, that is a mistake that we are correcting just now here. The second expression, the first index is I, which is a free index. Then the second term, the j is matching, so j is a dummy index, I is a free index, but the third term j is a free index. So, you have got free index as I in the left hand side, on the right hand side the first term it is I. So, we can correct this to make it also I, and then the expression will be valid. So, you can see that in each term the free index is I. However, the first term on the right hand side there is a summation that is involved, but otherwise you are basically writing, how many equations are we writing here? We are writing basically 3 equations, because the I can be taking values from 1 to 3. So, here also how many equations? 3 equations for each of j. So, here it is. So, the last equation here we have written the first term I is the free index. The second term j is a dummy index, I is a free index. So, the free index is matching for both the terms on the left hand side. So, that is fine. On the right hand side, the first term I is the free index. Okay, so, I is the free index till now, but in the last term j is the free index. So, which means that here is where the mistake is. So, we must correct this fellow and make that as fi. Now, you can see that in every term in this equation you have got I as a free index. Only thing is that here you have got a summation happening over the index j, but otherwise we are talking about essentially 3 equations, and these equations are written for I varying from 1 to 3. So, you can see that this is how expressions are being used to practice the subscript notation, which are very succinct. So, instead of writing 3 different equations where the second term on the left hand side has a summation, we have written a very concise form by using the subscript notation, and then 3 equations are written with just one equation where the index is kept to be free there. In this case, it is I is the free index. So, this is the, I would say, the power of subscript notation in being able to write a lot of things in a very succinct form. Okay. So, the subscript notation can then also be used to express things that we know, and to even do some derivations of vector identities, etc. So, here we see some terminology that is coming in. So, I want to make it familiar to you. So, whenever we saw that the subscript is coming in one term with repetition, we already mentioned that it is like a dot product. Now, the sense of dot product is usually for vectors, and when you go to tensors, we must use a term that a little bit more generic. So, we use the term which is inner product. So, inner product is basically contraction operation. Okay. So, what we mean by that inner means it is a contraction operation. What does it mean? It means that the number of indices are reduced in the expression. So, you could see that the expression here I and I, there are 2 indices, but they are reduced to 0 because it is repeated. So, this expression uses the contraction operation over the index I, and therefore, it is basically an inner product of 2 quantities which are vectors. So, this is nothing but what we already know from engineering mathematics. It is nothing but the dot product of 2 vectors A and B. Okay. So, the dot product is written as the 2 repeated indices, and it is written in a very simple form here. You could generalize this to any order tensor also, but for vectors we already know what it is, and you could expand this meaning to higher order quantities as well. When the quantity B is same as A, then you can see that the second expression is coming in, and we can see that this is nothing but the magnitude, okay, squared. So, what would be the magnitude of a vector u in subscript notation? So, we could see that it is nothing but ui square root, that is nothing but the magnitude of the vector u. So, you could see because ui and ui coming together would mean that it is basically a quantity like this, a dot product of a vector with itself, and that would then give you a square of magnitude. So, taking the square root, you get the magnitude of the vector u. So, familiar quantities like a dot product, a magnitude can be expressed using the subscript notation in the following manner. You could also use it, the idea of contraction operation can be used over quantities that are of higher order also. So, what are we doing in this expression? The index I is reduced and only the j is remaining. So, you could see that on the right hand side d is a bunch of 3 raised to power of 2, that is basically 9 quantities or 9 components, and on the left hand side c is a vector. So, there are 3 quantities. So, a quantity that has 9 components is being used to generate a quantity that has 3 components using this expression, and in this process what is happening is one index is lost and that has been contracted. So, you could see that dij bi has undergone a contraction operation over the index I, and then we are summing it up over the index I, and that summation is what is given in these equations. And you can see that there are 3 equations. The reason is that C is a vector with the 3 components. So, 1 equation per component. So, 3 equations are written in this form. So, you could then compare how much of algebra is written here, and all this is implied by just this expression. So, that is exactly the idea of subscript notation or the summation convention, giving you a very brief way of writing long expressions. So, just like there is an inner product which means it is for the dot product, a counterpart of it is outer product. So, outer product is basically a dyadic product. So, what we mean by that is as follows. So, when we were discussing about vectors, we knew dot product, we knew cross product, but when we generalize this concept, then we have what are called inner products and outer products, and inner product is matching with the idea of dot product in some way, but the outer product we have not used that in vector algebra, but here we can see how it could be used. So, here we have seen that a set of 2 vectors A and B, okay, A is a vector and B is a vector, but then what we have written here is a matrix of 9 elements made by using the elements of A and B. So, it is a dyadic product of A and B. So, sometimes people do write this in this following fashion. So, this is a operator, it is not a dot product or a not cross product, it is a dyadic product. So, which means that it is a special way of multiplying the numbers such a way that from 3 elements of A and 3 elements of B, we get 9 elements of a quantity, which if you want you can say it is for Dij. So, it is a matrix of 9 elements and each of those are related in this following manner. So, A I B J is a dyadic product of 2 quantities A and B. Now, this can be generalized to create higher order quantities from lower order quantities. What did we do in inner product? We have taken vectors and made them into a scalar, which means that we have taken higher order quantities and reduced them to lower order quantities. By order we mean the number of elements we require to represent it. So, here in the outer product we have done the opposite, we have taken lower order quantities, namely vectors, and then created higher order quantities out of them, namely the tensor in this case. Okay, so, there is a special quantity which has 9 numbers and has a very interesting behavior when we use it in multiplication, and that is called the Kronecker delta. So, Kronecker delta is represented here with 9 numbers, so 3 of them as unities and 6 of them as zeros. So, delta Ij is a very special second order quantity, and this can be used with special properties because it allows us to do multiplications because of its properties that it will take a value of 1 when I is equal to j and value of 0 when I is not equal to j. So, this particular property makes it possible to use in multiple ways. Let us see in what ways it will help us. Okay. So, let us look at the expression like this. Okay. A matrix A is given by this, okay, A11, A12, A13. So, this expression is nothing but a inner product of A with the Kronecker delta, and the contraction operation is over the indices I and j both. So, it must be giving us just one number, and we can see that this when we expand we only get 3 numbers because the delta has only 3 unities, rest of them are zeros. So, only when I is equal to j you have got a unity there. So, only those numbers will survive. So, what is the quantity that is written here? It is nothing but a summation of these, which is nothing but trace, okay, of a matrix A. So, this is the idea. So, whenever you take a second order tensor or a quantity that has 9 elements, a matrix that has 9 elements, and if you multiply with the Kronecker delta such that both the indices are being contracted, then the outcome is nothing but just the trace. Okay. And because there are no subscripts for this quantity, both the indices I and j are dummy indices. So, this actually is a scalar, which is something that is new for us to know, that is trace is a scalar. Okay. So, the meaning of this we will come to it in a later lesson, because it shows us what are called as invariant quantities of any expression, and here we are encountering that is something for the first time. Okay. So, it is also used, the Kronecker delta is also used to simplify expressions, so that the dummy indices can be modified. So, the way it is done is as follows. Because we know that delta is taking a value of 1 only when the two indices are matching. So, it implies that whenever it is multiplied with a quantity, the one index that matches is going to be then replaced. So, here we can see that I is matching. So, look at the way this quantity is done, I is matching. So, the remaining index, okay, is going to be used here. Okay. So, the j is going to be then replacing that index, and then you have got ajk. Okay. So, the way delta is used is to replace the indices of expressions. So, what we do is basically look at the indices. If delta has two indices, in this case I and j, see which of them is matching with the quantity and then put the other quantity there. So, this is matching. So, then j is used to replace. Okay. So, we are not touching the second index of A, okay, that is k, and the k we are not touching because the index k is not appearing in Kronecker delta. So, we are not going to touch that. The first quantity A has two indices I and k is not appearing anyway. So, we will not touch that. The first index I is repeated with the index of Kronecker delta. So, we see that the Kronecker delta has I and j. So, the I is matching. So, put the j index in its place. So, you get the quantity A j k. Now, this is an identity. What we mean by that is, this can be proven. So, you can prove it and do element by element and verify that. It can be verified by visual inspection, but if you are not convinced, you could actually do that element by element. How many equations did we write here? Basically, we have written 9 equations, because for each value of j and k, we have got one equation, and on the left hand side we have got a summation, okay, because there is an I that is matching index. So, with a summation of I, and only when of course I matches the index j, then you have got some number there, otherwise not. So, we got written 9 equations out there. Okay. So, look at this expression. How many equations is this? So, these are basically 3 equations. And what did we do? The transformation, we have done the transformation of indices the same way. The I index is matching with that of Kronecker delta. So, the j index is then going to be replacing there. Okay. So, that is why Pj has come. So, you could see that whenever we have a necessity to change the indices of some quantities, and if those quantities have Kronecker delta, then we are lucky, because the indices of Kronecker delta can be then used to swap the indices of quantities with which it will multiply, and that will be of great use later on when we are trying to apply the subscript notation to prove vector identities. Okay. So, this is how you can then apply the Kronecker delta and write the expressions simpler forms. So, the expression has more terms, that we can reduce them. So, what would be this expression? First expression. So, you could pick one of the two quantities. A has a subscript I, B has a subscript of j, and both of them are in Kronecker delta. So, we can take a pick. Let us take the index of B. So, the j is matching here. So, I will put the quantity there, okay, A I and then B I. Okay. So, you could see that this is nothing but the dot product of A and B. So, which means that a very generic way of writing a dot product is nothing but writing the two vectors with their respective indices and then multiplying that with the Kronecker delta with the same indices that are matching. So, if you want to write, okay, the dot product of ui and vk, then you would put a delta there and I and k. So, this becomes the dot product of two vectors u and b. Okay. So, delta is that way has a special property to be used in dot products. So, what would be this quantity? It is the same quantity that we have written here. So, you could see that from here to here, what have we done? We have essentially replaced the index of b from j to I. So, delta has the property to replace indices, that has been observed here. What about the quantity here? Mij delta ij. you could see that delta actually can be used to transform any of them. So, you pick the index, I want to pick the index j. So, then I would write it as m I, the other index is I. Now, this is something that we already know, this is nothing but m11 plus m22 plus m33. This is nothing but trace of a matrix M. So, you could see that the property of Kronecker delta is coming multifold. One way is in the dot product, another way is in getting the trace. Okay. So, for the dot product we have seen how it can be used, for the trace you can see how it is used here. And what would be this quantity? So, this would be 3, because then you can see that it is nothing but the trace of the matrix. So, here we have seen that when the delta is coming you are getting the trace of m, but the m is nothing but here the delta itself. The delta trace of delta is nothing but the diagonal element summed up, and that would be 3. So, you could see that these expressions are going to be helping us in reducing the number of terms. So, whenever we have got multiple deltas, we use these expressions to reduce the number of indices, and that makes the working with the subscript notation a lot easier. Okay, so, there is another quantity that I would like to introduce. We will take it up in the next session. So, at this moment we will stop and then continue in the next session.